Okay, section 4.2, cofactor expansion and applications of determinant. In this section, we introduce a method to compute determinant. First, we start with the definition of minor and cofactor. Suppose we have a matrix A, then the submatrix A of ij, which is obtained by removing the ith row and jth column of from the matrix A. So this is a n-1 by n-1 submatrix of A. Then determinant of this submatrix, Mij, is called a minor of A for Aij. Okay? And if we add this sign, -1, -1 to the I plus j, so this could be +1 or -1. If we multiply +1 or -1 on Mij, we call it Cij, which is a cofactor of A for entry Aij. So suppose we have a n by n matrix A, then we have n square minus and n square cofactors. All the difference is a sign. Half of them are plus and half of them are minus. Depend on the addition of I plus j. Okay. So if we have A, then since we know how to find the determinant of the submatrix, so we can find the cofactor. Suppose A is here. What's the minor and cofactor of A for 1, 1 entry of A? Okay. Then how? Okay, 1, 1 entry. Minor of this A, so 1, 1 entry. So here, delete the first row and delete the first column because it's 1, 1. So delete the first row and first column. Then what we have? We have this 2 by 2 matrix, which is this. Okay, you delete first row and delete first column. Then what's the determinant? It's a 16. Okay, and then what for cofactor? So we have M11, which is a minor of A for A11. What is C11? All we have to do is just multiply this, which is the square of -1, which is +1. So multiply +1 is the same, so it's 16. Okay? What about A12, the M12? What about M12? M12. So the minor of A for A12. So for this, delete the first row and the second column, isn't it? Then we have this matrix. Determinant of this is 16 minus 6, so 10. And -1 to the 1 plus 2 is 3, which is odd, so it's a minus. So actually, so cofactor is going to be -10. Okay. Adjugate. This is called the classical adjoint or adjunct. Some books are calling this is just adjoint, but later in the linear algebra, adjoint is used, self-adjoint. Adjoint is used for the other meaning. So it should be classified as a classical adjoint, or you should call it adjugate. Okay. Let Cij be a cofactor of A for Aij. Then the transpose of the cofactor matrix whose Ij entry is Cji is called the adjugate of A and denoted by adjugate of A like this. Okay? The classical adjoint of A. So the Ij entry of adjugate of A is the transpose of Cij, which is Cji. Here. The C12 goes because of transpose. If you can find C11, so finding this is find the C11, C12, so on this order, and form a matrix, and then take a transpose. So for find Cij, all Cij's, and form a matrix with it, and then take a transpose in the same order. Then C12 goes here, and C1n goes from here to here, I think, because it's a transpose. Okay. So find the adjugate of A for this. So find the C11, C12, C13, and the C33 like this. Then you form a matrix, and then take a transpose. So C11 is minus 18, C12 is 17. So 17 goes to C2, this 2-1 position. So 17 goes to here. And C13 minus 6 goes to here, transpose. Okay? And C33 goes to here. As you see, it's just the signs are plus. This is positive, is even, odd, even, odd, even, odd, even, odd. So these are all positive. Here, are all negative signs. So it's okay. If you define a matrix, then this command gives you an adjugate of a given matrix, which is same as what you found here. So if for any large size matrix, this command will give you the adjugate of the given matrix, or classical disjoint of a matrix. Cofactor expansion. Determinant of 3 by 3 matrix can be expanded as follows. Like A can be written as these 3 terms and these 3 terms with for the even permutations and odd permutations. This can be factored like this, isn't it? This can be factored with A11, A21, A31 like this, isn't it? Then what are these? These are cofactors, isn't it? These 3 terms. So this could be written as A11, C11 plus A21, C21 plus A31 to C11. This has some kind of coincidence, is it? Those numbers. Okay? So we call this, we expand this matrix determinant expansion along the first column, A11, A21, A31, like this. We did the determinant expansion along the first column. Okay. This is known as a Laplace cofactor expansion of A along the first column. Laplace found this kind of relationship. Okay. Since determinant of A is the same as determinant of A transpose, so the same thing could be done on the rows, because if you A transpose is just transpose of this matrix A, then this row becomes a columns. Column becomes rows. So everything work not only for columns but also work for rows. Cofactor expansion work not only for the first column, works for the second column and also for the nth column. And also this cofactor expansion works for the rows, first, second, third, and everything. Okay. So this is a very good observation. So that can be simplified in here. Okay. Next, for 3 by 3 matrix A, the following equality hold, following identity hold, like this. If you multiply the matrix A with adjoint adjugate of A, then that is same as this scalar matrix, whose main diagonal entries are all determinant of A. Laplace found this relationship. If you do check it, then what is the first entry of this matrix? This is the inner product between of the first column of this matrix and first row of this matrix and first column of this matrix, which is this, isn't it? A11, C11, A12, C21, isn't it? C1, A1, C21, A3, first row, 잠깐만. Okay. So A times adjugate of A, the one entity should be A11 plus C11 plus A12 times C12, because the 2-1 entry of adjugate of A is C12 and 3-1 entry of adjugate of A is C13, because this is the transpose of the Cij's. So as you see, these main diagonal entries are the Laplace cofactor expansion along the first row, second row, and third row, and nth row. So the main diagonal entries of this product of these two matrices are determinant of A. And off diagonal entries are, we can observe that this is a kind of cofactor expansion of a matrix whose two columns are same. So the determinant of those matrices are 0. So off diagonal entries are all 0 from the observation that we had in section 4.1. So we can easily check this. The product of these two matrices is a scalar matrix whose main diagonal entries are determinant of A. And determinant of this matrix is a nth power of determinant of A. Okay, for general matrix N. Okay. And this shows summation of the linear combination of the C, J K's are determinant of A or 0, depend on whether I is equal to J or not. Okay. This is actually full part of Laplace cofactor expansion for a general size matrix N. And okay, with this, if we define a matrix A and then find the determinant of A and also find the determinant of A times adjugate of A, then A times adjugate of A turned out to be a scalar matrix whose diagonal entries are minus 94, which is the determinant of A. If you define a larger size matrix, then you will see the same thing, same result, like what you see, which shows the above fact is true. So this is a summary of the earlier discussions. Suppose A is an n by n square matrix, then for any ij, determinant of A can be written as a cofactor expansion along the ith row for any ith row, and A can be written as a cofactor expansion along the any j's column. Okay, not only one row or column, it's for any rows and any columns. Okay. Okay. When we computing the determinant, it is advantageous to use cofactor expansion along the row column or column which has many zeros. Okay. Suppose we have this matrix. We want to find the determinant of this matrix. We know third type elementary row operation does not make any change on the determinant. Okay. So we do the third type elementary row operation a couple of times to make more zeros on the, so multiply minus 3 and add on the second row and add it to the first row, multiply minus 2 on the second row and add it to the third row, multiply minus 3 on the second row and add it for the first row, then we can make this 0, and this 0, isn't it? Then we can do the cofactor expansion along the first column. Then 0 times whatever is 0. Okay? So what's left is just 1 times minus 1 to the 2 plus 1 times the determinant of this 3 by 3 submatrix, isn't it? Which is this. So this is going to be turned out to be a very easy computation. That's the idea. Okay, the cofactor expansion can be used to find the determinant easily. Then determinant of this is 18, so minus 1 times the 18 is minus 18. And also let A be an n by n invertible matrix. Then the inverse matrix of A is this. Why? Because A times adjugate of A was the scalar matrix. So if A inverse exists, then multiply A inverse on both sides. Okay, then what happened? Then A inverse, A was gone, and A inverse was left. And determine and identity matrix. Divide both sides with the determinant of A. So determinant A goes to the left, goes to the right, so A inverse can be written in this way. Okay, do it again. Multiply A determinant of A on both sides, and A determinant of A goes here. Okay, and adjugate of A left. Multiply A inverse on right on both sides. Then this is turning out to be identity times the determinant, and A goes here. So A times the adjugate of A is the determinant of A times identity matrix. So that's what we had. So this is very easy fact test that we can have. So now we have another tool to find the inverse matrix. Okay? We can find the inverse by using the cofactor expansion with the adjoint adjugate matrix instead of Gaussian elimination. Okay? So for definer matrix, if we find the adjugate matrix of A and the determinant of A, then if you find the 1 over determinant of A times adjugate of A, then you have what? This. If you just find the inverse matrix of A, then that is this. As you see, they are same. It works for any matrix of any size, okay? Because we proved it. I think that's the end of section 4.2. Any questions?